Howdy, we finished chapter 4 and now we're moving to chapter 5 on gases. To study gases, we're going to have a firm understanding of pressure and really pressure on a microscopic scale. I've got a PHET simulation that's right here that's going to be helpful. But first, I want to show you that we're going to kind of ignore temperature and volume right now. We're just going to focus on pressure. Pressure is, say, imagine the point of my finger is one molecule, one gas molecule. It is moving and it's bouncing on the side of my screen right here. Boing, 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 boing. So there's two factors going on when my gas molecule collides with its container. How big the gas molecule is, or the mass of it, does play a factor in the pressure, but also the frequency. So if I bounce them back and forth, those collisions with the container would be more frequent, so that would have a higher pressure. If I had a giant, massive Andre the Giant finger, or a giant gas molecule, and it collided with it, you get the idea. The more the mass, the more pressure would be exerted. So when I look at the simulation, we're going to still ignore kind of the temperature and the volume right now. I want you to watch the pressure gauge as I give it one pump and I put some gas molecules in there. Are they all going the same speed? Are they all colliding with their containers? No, they're not all going the same speed, but remember, speed has to do with temperature, and we're kind of putting that to the side right now. But they are all colliding with their containers. And imagine these little red balls as like little ping pong balls. It doesn't make a huge difference when they collide with their containers. We get 0.22 atmospheres is our pressure. So, and I want y'all to notice that if I add more molecules, or give it a couple more pumps, it will now the pressure will now increase as it goes up. So they're directly related. The moles and the pressure are always going to be directly related. That was on the AP test last year. So as I can also increase them and have them jumbling around. So we'll reset and we'll go to a heavy species now. So if I give it one pump, you see they're moving a lot slower. They're heavy, and they're a lot bigger. So these would be like your bowling balls. They're going around and they're colliding. They're still colliding with about the same amount of frequency, maybe, but they are, I'm sorry, they're colliding with less frequency, but they have more mass now. So that's why they're exerting just about similar pressures. Less frequency, but now they have more mass. So we've got more bowling balls now flying around. So you could increase some more just like that, and the pressure will now go up. Another way you can see gas pressure is by a diagram that looks just like this. These little purple orbs represent gas molecules. It can be any color you want, but they also all have one arrow. The arrow shows two things. It shows the direction and it shows the magnitude. That comes from a physical term and called the vector in physics. That's the first thing you learn in a physics class. And it shows the direction, and you can see they all have their own independent directions, and the length of the vector, or the length of the arrow, indicates the velocity of the gas particles. So that's how we would show those in a diagram form. The way we measure pressure in real life is by using a barometer. I've got one in my classroom, and it was developed by an Italian guy named Evangelista Torricelli. He was looking. The story with this is that he was just kind of experimenting with some mercury in a tube, and he would pull a vacuum in this tube here and leave it sitting down here. And he would travel to different places in Italy that were all at different altitudes, and show it to different people. But what he noticed was this line would move depending on which place he was in. And it would always move to some independent place, and it would be about the same place every time because they were about the same altitude, and the atmospheric pressure doesn't tend to change very much. It only changes during a storm or something like that. Another way we can actually measure pressure is by using a manometer. And here's a picture of it here where we have a U tube. No, not like the YouTube channel. I mean like the letter U, tube. And that's what this is here. And you can measure the height difference. If there's a great atmospheric pressure, then it will push down the liquid. Commonly mercury. Mercury works well in this example. Or if there's a low atmospheric pressure, then or lower than the gas pressure that's in the sample, then it will be higher than that. The way we measure pressure is by using these units. You'll need to know that since Torricelli was the guy who discovered this on accident. It's funny how scientists tend to discover things on accident. And he used mercury, so we call 1 millimeter of mercury as 1 torr. This is the most common one that I've seen in real life, and that's the one I always used. So I'm familiar that it's 760 millimeters of mercury, or 760 torr, is 1 atmosphere. That's about where we normally are at the time, and that's where the barometer in my classroom will read. Another thing is the French unit is called kilopascals. That's French, and it's not tested on the AP test, thank goodness, because it makes sense because it's measured in newtons per square meter, which means amount of force applied to a certain area. So it's basically the unit of force divided by the surface area that you actually have. So it makes sense to have it, but it's not easy to use, so we don't really use it. We use 760 torr is usually what we use.